Okay, so in the last class we have seen this properties of a net flow. If we have f a net flow, then f of x comma x is 0, then f of x comma y is equal to minus of f of x y comma x, and then if we have a two disjoint set f of x union y, then this is basically sum of this. So, this we have proved in the last class. Now, we just want to use this to have a theorem which is related to the value of the flow. So, this is basically the value of the flow. So, basically it is telling, the theorem is telling, we have given. So, value of the flow is basically f of v comma t. So, it is the total flow which is receiving at the sink point. So, this we have to prove. Now, we know the what is the value. So, how to prove this? So, we know what is the value of the flow. We know the value of the flow is basically the flow which is passing out from the source. So, we have a source here. So, this is basically the flow which is passing out from the source, and this is the net flow. So, this is basically summation of s of s comma v. So, this is the definition of the value of a flow, because here f is net flow, not the positive flow. If you have to take positive flow, then minus of that, but here we are dealing with the simplifier notation which is net flow. Okay, so then how we do that? So, this we can write f of v comma v, because f of v comma v is 0, just now we have seen, then f of v minus s comma v, because so this is basically, we can omit the brackets. So, this is coming from these properties we have discussed. So, this is nothing but f of v comma v minus s. Okay. So, now this we can write as f of v comma t plus f of v comma v minus s minus t. So, this is the way we define this. I mean, we are using the last three lemma we have discussed. So, this is nothing but f of v comma t. So, this is the proof. So, that means whatever the flow we are passing at the sink source, that will be absorbed in the sink. So, that is the property we want, and that is quite obvious now, because we want to say this is the network, we want to pass the current. So, we want that whatever the current we want to pass from here, net current, that should be absorbed here, and that is the value of the flow, and this is the theorem is telling that will be absorbed there. I mean, that will be passing at that end sink. Okay, now, if we take this example, so what is the net flow? What is the value of the flow? So, value of the flow for this network. So, this is a network, we have these are the basically capacity, and these are basically positive flow. In the example we have discussed in the previous classes, we discussed these are the positive flow. Now, what is the net flow? Net flow is basically after we cancelling the flow cancellation. If so, we assume the without any loss of generated, the flow flow will be only one direction, from u to v, not from v to u. If there is a flow, say earlier it was 2, it was earlier the positive flow 1, it was 2, it was 1. So, what we did, instead of flow in both direction, we just want to flow in one direction, and we are just talking about net flow. So, net flow is 1, because this was cancelling out. So, this is the flow cancellation we did. So, effectively we have this net flow. So, then what is the value of the flow? So, value of the flow is the flow net flow you are passing from this. So, this is basically 2 plus 2, it is basically 4. So, this is basically summation of f of s comma v, v is from this. So, this is basically 4. So, this is the value of the flow, and now we can check what is the flow at the sink. Flow at the sink is basically 2 plus 2. So, 4. So, this is the example of this theorem. So, whatever flow we are passing from the source, that will be going to the sink. Okay. So, this is the way. Now, we defined another concept which is called cut, flow cut. I mean, so cut. So, what is the cut? So, let us okay. So, okay. So, let us just define the cuts. So, this is definition. So, a cut S T, this is to set S and T, capital S and T of a flow network G, which is basically V comma E, is a partition of V such that the source belongs to S and the sink belongs to T. So, any such partition, basically we have a graph G and we are taking a partition, that means we are dividing the vertexes are there V. So, this is the V vertex. So, V is basically S union T and this is the disjoint set. This is the disjoint partition and such that S will be here and T will belongs to here. So, this is the property. So, we take a class, we take a capital S from using this, I mean, which containing the source S, and we take another set capital T which contain the sink T. So, this is where any such partition is called a cut. Any such partition is called a cut. Okay. So, for example, so this is a cut. Now, how we define flow across the cut? So, suppose we have a cut here. Now, if F is a flow, flow means we now means the net flow always, because we simplify the notation, flow on G, then flow across the cut, flow across the cut is basically f of S comma T. This is how we define the flow across the cut. Okay. So, the total flow across the cut. So, that means basically, so f of S comma T is basically nothing but summation of double sum S of u comma V, where u is belongs to S set and V is belongs to T set. So, basically we are partitioning V, total vertex is V, we are partitioning into two parts, S set, T set. Now, there are H from u to V, I mean one part is in S, another part is in T. We know S small s is here, we know small t is here. Okay. So, now this is basically sum of the flow from one set to another set, where these are called bridge edge, like one vertex is in S, capital S, another vertex is in capital T. So, we take the sum of all such flow and that will give us the the total flow, that will give us the flow across the cut. That is how we define this. So, let us take some example over here. For this network, say so these are the, so for this network let us take some example. Suppose this is our source and this, suppose our S is basically, these are the set in, so this is S. Yeah, so basically these two vertices are in S, say. These are in S and remaining all vertices are in T. We can take any cut. This is one cut. Only thing we need to consider that this is a partition and the source must be in capital S and the sink must be is capital T. So, that is the only thing we need to take care. Now, what is the f of S comma T then? So, f of S comma T is basically summation of all the vertices, all the flow between the edges such that one edge is in S and another edge must be in T. So, what are the edge basically who are in edge? So, this is one edge, this is one edge and this is one way. So, this is basically -2 will come, then this is coming from here to here. So, what is the flow from here to here? So, this is basically flow is 1. So, the flow from here to here is -1 because this is the Q symmetric property of the flow. And there we have a flow from here to here to, so any other vertices are in capital T. So, here to here 2, here to here, here to here it is basically 1. So, it should be yeah. So, now we consider all the vertex from this to this. So, this is nothing but 2 plus 2 for these two vertex, for this and this, and then from for we take this node, from this node this is the 2 plus 2 and this is another edge, but this minus of that is 0. So, there is no contribution. Now, we take another vertex from S, capital S. So, this vertex, for this vertex, so we have this is the flow from this to this is basically -2, then we have flow from this to this is +1, flow from this to this is -1, and then we have flow from this to this is +2. So, this is basically coming out to be 4. Okay. So, this is basically coming out to be 4. So, that is the, that we know the value of the flow. So, this is the result. So, if you take any cut and it will basically give us the value of the flow, if you take any cut. So, that is the theorem we are going to show. So, this is the observation. So, not only these two, you can take any vertices and it will work. So, the observation is, so if you take any cut, so this is the lemma. So, for any flow f and any cut S comma t, we have the flow value of the flow is basically the value of the flow across the cut. So, this is basically S of f of S comma t. So, how to prove that? So, you have seen through this example. So, So, if you take these two vertices in S, then the value and other in T, capital T, then the value of the flow across the card, this card is 4. Not only this, we can take any other partition and we can see the value of the card is always 4, and that is the value of the flow. Okay. So, how to prove this? So, basically f of S comma T is nothing but f of S comma, we will use that properties f of S comma V minus f of S comma S, because V consists of S union T, and S union T are disjoint. So, we know this property f of we know this property na, f of S comma, this is basically f of x comma z plus f of y comma z. So, we are using this where S x y are disjoint. So, by using this we can show this. Okay. So, this is 0, this we know, f of x comma x is 0. So, this is basically f of S comma V. Now, again we can write as f of S small s comma V plus f of capital S minus small s comma V, again that property of disjoint property. So, this is nothing but f of S comma V. So, this is basically the value of the flow. So, this is the proof. Okay. So, if you take any card, then that will give us basically the value of the flow. Okay. So, now we define the capacity of a flow. So, capacity across a flow. So, this is basically sum of the capacity on the edges in the flow, sorry, capacity of a cart. So, capacity of a cart. So, how we define that? So, for example, so if we take this flow network where these are the vertices in S and other on T. So, the capacity of this basically the capacity. So, we add up the capacity of each of the vertices. So, this is basically we denote this by C of S comma T. This is nothing but summation of double summation of C of U V, where U is belongs to S and V is belongs to T. So, this is here. So, if you do this 2 3 plus 2, then plus what are the values going 1 plus 2 plus 3, 1 plus 2 plus 3. So, this is basically 11. So, this is the capacity of this cut. Okay. So, now we are having, we want to use the cut for. So, basically what we are looking for? We are looking for max flow. We have a network, we want to flow maximum current. So, max flow. So, for that we are bringing this cut, and we will see that there is a relationship max flow with the capacity of this cut. So, that will give us a algorithm basically. So, mean cut max flow. So, let us just write that theorem. So, this is sort of upper bound of the on the max flow. So, the value of any flow is bounded above by the capacity of any cart. That is important, any cart. So, the value of, so max value of the flow. So, this is the upper bound. Okay. So, how to prove this? So, let us take a cart over here, say S comma T, be any cart. Now, we have seen the value of the flow is nothing but value of the flow across the cart, and this we know this is basically summation of f of u comma v, v belongs to S and u belongs to S and this v belongs to T. Now, this is the flow. So, this must be less than all the capacity on that H. So, this is basically summation of double summation of C of u comma v, and this is nothing but our C of S comma T. So, this is the proof. So, this is the proof. So, this is the basically the value of this. So, now we define another concept which is called residual network. And that will give us the one algorithm to find the max flow. So, this is the last concept, and then we will talk about augmenting path. So, this is the definition residual network. Okay, so what is the definition of residual network? So, suppose we have given a flow, let F be a flow, net flow on a flow network G, which is basically V comma E. Okay. Now, we defined a residual network. We define the residual network which is another graph which is denoted by GF and whose vertices are same, but only thing for the H we have E of F, because this is having different edge weight and we may have edges also different. So, this is a graph, directed graph with strictly positive residual capacity, with strictly positive residual capacities. So, that means C of F of u v is equal to C of u v minus F of u v, which is basically greater than 0. So, for example, and so that means, so if we have a vertex u, so this is our G. So, suppose there is a u v. So, suppose this is the situation 0 to 1. So, this we are dealing with the say positive flow 3:5. So, suppose this is our original graph, part of the original graph u v. Now, in the residual graph we have same vertex u v, but only thing we are changing the edge. How we are changing the edge? We want to see how much more current we can send, how much more flow we can flow on that. So, that is the idea. So, how much more current we can pass. So, that is the thing. So, that will become in GF basically this will become like this u v. So, how much more current we can pass from this to this? This capacity is 5, we have 3. So, we can pass 2, and then from this to this we have so from this to this is the net flow. So, this is minus 3 and the capacity is 1. So, 1 and then minus of minus 3. So, this is 4. Okay. So, this is the basically. So, that means 4 unit of current we can flow here and 2 unit of current we can flow. So, that means this E of f is basically admits more flow. So, how much more we can flow? More flow. So, how much more current we can pass in there. So, this is the thing. So, now we will define. So, the lemma is basically so this is a lemma. So, this is basically number of h must be twice of number of this. So, now we will define augmenting path. So, this is basically path for this residual graph. Okay. Now, how we define this definition? So, any path from S to T in GF is an augmenting path in G with respect to the flow F. Okay. So, then we can just write that C of F p, the flow value can be increased among, because this much. So, we will take an example. So, C of F p is basically minimum among this Cf of u v, minimum among the capacity in that path, and that minimum we can pass. This is the more value we can pass on that path. So, we will take an example. Let us take an example. Suppose we have in the original graph we have, say this is S and we have some vertices. So, this is, these are the 0, 2, these are the capacity and the flow. So, 5, 5. So, this is T, say 2, 5. So, suppose this is a path from S to T in the original graph. Now, what will be the path from the in the residual graph, that is called augmenting path. So, in GF, how do we draw GF? So, GF is basically this is S. Okay. So, now how much more flow we can put from here to here? 2. Okay. Now, from here to here we can pass 3. Now, how much more we can pass here to here? 4, and here to here 2. Now, here to here how much more we can pass? 2, and this is basically over all we have used. So, there is no way, and then this is basically here to here, no, this is basically 7, because this is 5 current is coming. So, this way we can pass this 5. So, this is minus 2 minus of minus 5, this is 7, and here to here we can pass this 2, and here to here still we can pass 1, and here to here we can pass 3, and here to here we can pass 2. So, this is the augmenting path from S to T. So, any path from in the residual graph is called augmenting path. This is the augmenting path. Now, what is the minimum minimum capacity in this path, minimum capacity is 2 here in this way. So, that means this 2 value we can easily pass more on this network, on this path. So, that is the idea. So, that will give us a theorem. So, this is called min cut max flow theorem. So, this theorem will have a give us a algorithm. So, max flow we are having, so, 2 minutes. Okay. So, we will just state the theorem, we are not going to prove this theorem in this course. So, the following are equivalent. The following statement are equivalent, or following are equivalent. What are they? So, if F is a max flow, then F admits no augmenting path. That means, because if there is a augmenting path, we can pass some more current there. So, that means it is not a max flow. Then this is basically C of s comma t for some cut. So, there exists some cut. So, this is the theorem, and there is an algorithm called Ford-Ferguson algorithm based on this theorem, which is the algorithm to finding the max flow. So, this algorithm is based on this theorem. So, we are not discussing this now, but this will be, this theorem, this algorithm is based on the theorem, and we are not proving this theorem in this class. Thank you.